Our next topic is subbasis. Let's see this definition. Let X be a set. A subbasis for a topology on X is a collection S of subsets of X such that the union of the elements in this collection equals X. That means S is a collection of subsets of X, so that if you take the union of all those subsets, then you get X. Such a collection is called a subbasis for some topology on X. But what is that topology? That comes next. The topology generated by this collection S is defined to be the collection of all unions of finite intersections of elements of S. It's a bit difficult to understand this part. Okay, so we need to go a bit more slowly. What are we doing here? We first of all have the collection S in which we have some subsets of X. And then what we do, we consider all possible finite intersections of elements of S and collect them together. And then from that collection we form all possible unions. This time finiteness is not necessary. That collection of unions is the topology generated by this subbasis S. We need to verify this, of course. So we are going to do that next. We first give the collection of all finite intersections of elements of S a name, B. Let B be the collection of all finite intersections of elements of S. So that means in terms of B, this topology is the collection of all unions of elements of B. Now you recall a previous result, namely that one which says that if you have a basis and if you have the topology generated by that basis, then the topology is simply the collection of all unions of elements of B. Now this collection which we are claiming is a topology is just that, the collection of all unions of, but we don't still know whether this is the basis. So if we can prove that this is the basis, then by the definition of this collection like this as the collection of all unions of that B, and by that result it will be proved that this is a topology, and in fact this B will be a basis for this topology. So everything now ultimately comes down to proving that B is a basis. That's it, and this part is easy. So let's see how we can do this. To prove that B is the basis for some topology on X, of course we have to verify those two conditions that we have in the definition of a basis. The first of which starts by taking any element in X, the state. Now what is it that we know about the subbasis? That the union of the elements of that subbasis is equal to X. So that means since this point X is in X, X will belong to that union. So X will belong to at least one element S from this collection S, because X is the union of all the elements of this collection. So at least one element of the collection would contain this point. Okay, and now finally note that S itself is an element of B as well, because what is B? B is the collection of all finite intersections of elements of S, of this collection S. So if you take a single set from S, that is itself also technically speaking a finite intersection. So you have got an element in this collection B which contains that chosen point, and this is the first condition for a basis. And next we go for the second condition. To prove that the second condition is also satisfied here, we take two elements B1 and B2 in that collection B and a point X in their intersection. What is it that we have to show here? We have to show that then there exists a B3 also again in this collection which contains X and which is itself a subset of this intersection. Actually what will happen here is this. this itself will belong to B, so that this intersection itself can play the role of that B3. So that's what we next are going to show. Now what does it mean for B1 and B2 to be in B? Because B is the collection of all finite intersections of elements of that collection S. So B1 and B2 are both such finite intersections. So that is why there will exist finitely many sets S1, S2 up to Sn, and again finitely many sets. These two numbers m and n need not be the same, of course. S1 prime, S2 prime up to Sn prime in that subbasis S, such that B1 is the intersection of these S's and B2 is the intersection of these S primes. Okay, now then what is B1 intersection B2? It is just simply this, which is also after all a finite intersection of elements of that subbasis S, and that is why by the definition of this collection B, this belongs to B. So you are searching for a B3, this itself is your B3, because B3 contains X, the point X, and is contained in this intersection because it is the intersection. And that's how you have successfully proved that this B is a basis. So it will generate a topology, but by that result, that topology is equal to the collection of all unions of elements of B. But the definition of this topology generated by the subbasis is also precisely that. So that is how our collection, the thing that we are calling a topology, is actually a topology. And that completes this section. The power is gone. That completes this section, and after that there are exercises that we will start solving from the next week. So see you next week on the same day. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.